Hello, my name is Christine G. Welcome to the BEC1 Applied Healthcare Statistics webinar overview. That's a mouthful. This one is on Chapter 3, which deals with the key principles underlying statistical inference, probability, and the normal distribution. And here I have a graduation picture. I like to put these up for my recordings. So you can see that there is light at the end of the tunnel. I am all the way to the left, and these are other ladies that I was hired with that are still here at WGU, and we had the same start date back 2005. So nice ladies, and we always have a good time at graduation. It's just so neat, and there is a light at the end of that tunnel, and hope to meet many people that can come out and attend it. So hope to see you there. And let's go ahead and get started with our content. And the first thing that we are going to be looking at are the properties of normal distribution of z-scores. So here we have a curve, and underneath the curve lies 50% of the data on this side, and then the other 50% is on this side. And right here, smack in the middle, is what we call the mean. And when we standardize it, we put it as 0. So you can have a mean that's 150, but when we standardize it, we say that the mean would be in the center here, but that it's 0 standard deviations away from itself, or away from the mean. And here, this would be 1, 2, and 3. And then to the left, so these are all positive standard deviations, and to the left is negative, -1, -2, -3. And here we have the total area under the curve is 100%. It contains 100% of the data. And notice that even though this side is negative, the area under the curve is positive. Area is a positive thing. It's never negative. So 50% and 50% adds up to 100% of the data. And these are, to the left and right, are the standard deviations. I'm just going to abbreviate that. And you'll notice most of the data is in the middle, right? So it's centered around the middle. It's symmetrical, meaning if we folded it in half, right here, it would lie on top of itself. It would be line up completely with itself, and there'd be no lines or points outside of it. It would fold on top of itself. So let's go ahead and look at our next slide. So here we're going to break this down a little bit further. Now we talked about in the last slide about having the different, let me see, the mean we know is here. It's always in the center, in the middle. The mean is the average. And then here we have 1 standard deviation, 2, 3, and then to the left of 0 is negative. -1, -2, -3. Now, what we can look at is this yellow part actually within -1 and +1 standard deviations encompasses 68% of the data. And then we have, let's see, from here to here under the curve encompasses 95% of the data. So if you're taking a sample, 95% of a normal distribution, 95% of the data would lie within -2 and +2 standard deviations from the mean. So let me just put this here, standard deviations. And then finally we have this between -3 and +3 standard deviations away from the mean. would be 99.7% of the data. So almost 100% of the data is between -3 and +3 standard deviations away from the mean. Okay, so now let's go ahead to the next slide. And this is just summing up some things, and I thought it was a good point that the book makes. So I wanted to highlight this. Know the uses that z-scores serve. And the z-score measures the number of standard deviations that an actual value lies from the mean. So that's what we were just looking at, 1, 2, 3, and we also looked at -1, 2, -3, and 0. 0 being where the mean is. And then you can also have values in between those as well. But normally we're just breaking it down into the discrete numbers, or the 1 to no decimals. So here we know that they can be positive or negative if you go to the left or the right of the mean. And to the right of the mean is positive because the mean is at 0, and to the left would be negative. And knowing probability about someone scoring above, below, or at the mean can be useful information. And that's kind of something to think about, that really when you're doing the data analysis and stuff, that this information tells you quite a bit about the sample, and you may make conclusions or see trends and get valuable information from this. Now, this information was all out of the Monroe e-text that I had copied here. So, okay, now we have a sample problem that I made up. My youngest son plays on the Rancho Santa Fe Attack soccer team for the boys U17. And it is said that the average number of calories on that team, daily intake of calories, was 3,000 calories with a standard deviation of 400 calories. Now, the mean goes in the middle, okay? And here we would have the mean is right here, 3,000. Well, I told you earlier the mean was 0. Well, when we standardize it, it's 0. And if we go to the right, 1 standard deviation, well, we know that the standard deviation is 400 calories. So this would be 3,400 calories. And then if we went 1 to the left, it would be 2,600 calories. Let me put calories here and standard deviations. And then here we could go -2. Oh, well, let's talk about this first. If we had this amount, this is between +1 and -1 standard deviations from the mean, and that would give us 68% of the data. So 68% of the boys on this team ate between 2,600 and 3,400 calories daily. And then if we went further out, we could do, so this would be 2,200 calories, and then this would be 3,800 calories. And between -2 and 2 standard deviations from the mean would be 95% of the data. So 95% of the boys ate between 2,200 and 3,800 calories. And then if we went out 3, so -3 would be 1,800 calories. These are growing boys, so it's very unlikely that they're eating less than that. So, and then this would be 4,200 calories. So, anyway, hope that makes sense, just to give you a look at things. And when we standardize things, though, we have 0 for the mean, but this is just to illustrate how it all works. 0 is in the middle, just like this is the actual mean that's in the middle. Okay. All right, now we are going to take a look at how to compute and interpret z-scores a bit further. So on this, we have an example. The ages of 62 women who participated in a program range from 10 to 22 years and are roughly normally distributed. The average age is 16 with a standard deviation of 2.94. What is the percentage of girls 18 and younger? So what we want to look at is we have that the average age, or mu, is 16, and the standard deviation, also written as sigma in this formula. So we have this formula here. Sigma is standard deviation, so we'll put 2.94. And then what is the percentage of girls 18 and younger? So 18 is our data point. So now we're going to substitute in and get our z-score. So z equals 18 minus 16 over 2.94, which equals, so I can do this in my head, 18 minus 16, 2, divided by 2.94. Now I can't do that in my head, so I have to put this into my calculator. 2 divided by 2.94, and I'm getting 0.6800272. Okay, so now what I'm going to do is it's asking me for the percentage of girls 18 and younger. So there are a couple of things that I want to look at. So I know that the data is normally distributed, and I know that the mean is, let me see, 16. And I know that I'm looking at an age of 18, but the standard deviation is 2.94. So I add 16 plus 2.94, and I get 18.94. So this is one standard deviation away from the mean. And this should be symmetrical, by the way. I'm just trying to standardize this. So 18.94 would actually be one standard deviation away from the mean. Now this is 0.680272. I'm going to round it off to 2 decimal places, and I have z equals 0.68. Okay, because I have 0 to the right of 8, and 0 is going to round down, so just stay the same, 0.68. Now, I know that 0.68 is between 0 and 1. So it's around here, 0.68. And I know that 18, my data point, is like about here too. So it's the same thing as this 0.68. This is my z-score, or how many standard deviations away from the mean my data point is. So now what I need to do, because I want to find out what this whole area is. Okay, so I'm going to need to look up, and you're going to need to do this too. This is going to be on the exam. You're going to have a z-table, and the one that you're going to be using is the one in Appendix B of your e-text. Now, I do know, what do I know? I know that this is 50% of the data. From here, the mean to the left. We know this is 50%. Now, what I need to find out is what this is, right? Or what this is right here. So now I'm going to have to look that up, and let me get that out. And okay, so here is the area. This chart gives us percent of total area of the normal curve between a z-score and the mean. So we look at our z-score that we calculated, and that was z equals 0.68. And so we go to 0.6, and then we go over to 0.8. Okay, so let's take a look. I have to draw the line or I'll mess it up. And you will have the chart like this on your exam. So 25.17, that's the percent of the data that's between the z-score and the mean. So let's go ahead and, so 25.17% would be, let me do it in red, I'm going to, 25.17% of the data is there. And same here. It's the same thing on both of these with the area under the curve. So here, what I'm going to do is to figure out what is the percentage of girls 18 and younger. Well, here's 18. So the area of the curve below 18 is 50 plus 25.17. And I add those two together and I get 75.17% of the girls are 18 and younger. So that would be my answer. Hope that that one makes sense. Okay, now on this one, we need to know how to convert a z-score to a raw score. So we're given information in this example with 62 women from ages 10 to 22. The data is roughly normally distributed. The average age is 16. Standard deviation is 2.94. So let's do this. Mu equals 16. Sigma is the standard deviation equals 2.94. And then the z-score is this guy. So when we substitute in for z, we're going to put 1.02041 equals, and then the mean, well, we don't know what x is, so x is our data point, but we don't know, we're looking for that raw score. Our mean is 16, population mean, and then 2.94 for our standard deviation. And now one of the things I can think about is that this is just barely over one standard deviation away. So it is like one would be here, and then that would be very close, 1.02041. And when I look at this, 16 is my actual mean, and one standard deviation away from that would be 18.94. And this is a little bit more than that. So I know that my number, my raw score, or this age, is going to be a little bit more than 18.94. So that's kind of nice to have that as an, way to check yourself on it. But let's take a look. So we want to solve for x. I'm going to need more room. So this is an equation. And in an equation, it is like a balance or a teeter-totter. So what you do to one side, you do to the other to keep the equality. Like if I add 1 pound on this side, I have to add it to the other. Otherwise, I'm not keeping my equality. It's going to be unbalanced. So here, I want to get, right now, 2.94 is dividing x minus, the quantity of x minus 16. And I don't want this fraction. I want to get rid of it. So what can I do to get rid of it? Well, I do the opposite of division. So I multiply. And I multiply this side by 2.94. Why? Because that number is in the denominator, and I want to be able to cancel it out. And what I do to one side, I have to do to the other to keep the equality. And then, let's see, I take my 2.94 and I times it by that. 2.94 times 1.02041, and I come up with 3.00001, and I'm just going to put it in as 3. I'm going to round it. Then on this side, what happens here? 2.94 divided by 2.94 is 1. 1 times x minus 16 is x minus 16. And then it's being divided by 1. X minus 16 divided by 1 is just x minus 16. Then I'm going to solve for x. I'm going to get x by itself. Right now, x is being subtracted by 16. I do the opposite and add 16. What I do to one side, I do to the other. This negative 16 plus 16 is just 0. X plus 0 is just x. So I have x equals 19. So that is my raw score. So this would be 19, and that makes sense because it's a little bit more than 1 standard deviation away from the mean. And we know 1 standard deviation away from the mean is 16 plus 2.94, so 18.94, and 19 is a little bit more than 18.94. So hope that makes sense. All right, now, so here you're asked to know the definition of probability and its characteristics and understand how probability links populations and samples. Well, a couple of things. We know the percentages on here. So we know that most of the data is going to tend toward the middle. And this is 68% of the data. And then as we go a little bit further away from the mean, we get 95%, and then all the way 99.7% of the data is within 3 negative and positive 3 standard deviations from the mean. And samples help to make predictions about the population. It doesn't make sense to go out and survey everyone, except, every 10 years the government does that in the census. But it's not that practical, and to get good data, you can do that by getting good large samples of groups. So this is also, it can be helpful to determine, drug testing trials, see how effective drugs are. You can take a sample and try and determine how it would affect the population from the way it affected the random sample. And a probability basically tells you how likely something is. So here it's basically telling us in this normal distribution that 68% of the time you're going to fall in here, within the mean by negative and positive 1 standard deviations from the mean. And if you were a betting person, that would be extraordinary because you'd be winning 68% of the time if you chose, the sample 68% of the time, and you made bets that it's going to fall within here, and somebody bet against you, and you'd be winning 68% of the time, which is more than 50% of the time, which is really good. So anyway, so I hope that sheds some light on things a little bit. And let's go on to the next slide, where we're just going to be looking at computing a probability of obtaining particular scores from a distribution. So, and most of this, all of this is from the free response questions of the study guide. So I'm not going in depth to things that the book may go into. So you do want to be reading in the e-text as well. But this is just the free response overview. So definitely good to understand this stuff. So here we have, so if we wanted to compute the probability that someone is married from this particular frequency chart, frequency distribution, probability that someone's married, well, this is just 21 out of 39, but we would want to reduce this fraction And we know that 3 divides 21 and also divides 39. And 3 divided by 3 is 1, so we're just changing the amount of pieces and not changing the value of the fraction. So this would be 7/13. So this is the probability that someone in this frequency distribution is married. And then that's just simple probability. And then if we had something like the probability that someone is married or single, you can look at that. So married or single, that would be married is 21/39, and then single is 7/39. So either one of those would work. So we would add them together. And we'd leave the denominator common. 21 plus 7 is 28/39. And we don't have a common factor, so we can't reduce. Here we could reduce, here we couldn't. Or this is after we reduced. So this is how we would obtain probabilities from a frequency distribution. And okay, next item. Let's go ahead to the next slide. And I've been talking about this throughout. So here, we talked about the sample we had with the boys soccer, where we have the normal curve and the standard normal curve. So with the normal curve, we put that the calories was 3,000, and then we put, when we standardize the normal curve, 0 is the mean, and then 1, 2, 3. And then we go to the left, -1, -2, -3 standard deviations. And then here, this would be 3,400, and then 3,800, 4,200. And this just shows us the actual numbers, whereas this shows us the z-scores or standard deviations from the mean. So, and I try to go over this quite a bit in the application, so you would be familiar with it by the time we got here. So hopefully that makes sense, and we know all the percentages and stuff. If we just looked here, I've always been saying, within negative and +1 standard deviations, and we know that from here to here is 68% of the data. And so half of 68% would be here, right? And so that would be 34% of the data's here. And then you can look at it that way too. So, and you can break it down further and further. And we know that 50% of the data is to the left of the mean and 50% of the data is to the right. So, okay. Let's see the next one. Okay, so this one, so we're going back to an example we used a bit earlier, and we are going to find a particular probabilities, so, or percentile rank, it looks like, and z-scores. So we know about this team, the boys U17 soccer players from Rancho Santa Fe Attack, and they typically have an average calorie intake of 3,000 calories with a standard deviation of 400. What is the z-score for the players who are eating calories in the 91.15th percentile rank? Okay, so what we can do is we can think about this a couple of ways. So I like drawing. I find a lot of students like visuals. Wish I had more room here. So let's say that we have, this is 91.15 percentile rank. So we know that it's to the right because we know that 50% is down here. And this is over 50%. So it's it's over here someplace, okay? And in order to, this is 91.15th percentile rank. So we know that we could look at a z-table and figure out what this would be as far as the 91.15th percentile rank. So we do know that underneath the curve, we would go up to 91.15%. So here, 50, we can subtract it. So 91.15 minus the 50%, and then we would come up with, let me see, 41.15% of the data would be right here. So this is the mean, which would be 0. And then, here we're including all of this, and we don't know what the z-score is here. Okay, this is what we're looking for. And then we know in our tail here, this would be like 8.85% of the data would be in this tail. So I didn't draw it very accurately, okay, because the tail looks pretty big. And it should be symmetrical and everything like that. This is just to give you a rough idea how things work. So we don't know what this is, but we can look up in Appendix B, and let me get that. And we know that the 41.15% is what we're looking for the area under the curve, because this gives us the percent of total area of normal curve between a z-score and the, that should say mean. And 41.15% is right here. Okay, I cut this chart off a bit. So the z-score on it would be 1.35. So now what I'm going to do with that is I know that that's my z-score. So I put that in here. I'll put it onto my 0.35, onto my diagram. So 91.15%, the 91.15th percentile rank falls when the z-score is 1.35 away from the 0. So that gives you 91.15% of the data. So, and what that means is that there were only 8.85% of the kids were eating more calories than that amount at that, and that the rest were below. So hope that makes sense. And then it's asking, what is the average calorie intake at this rank? So that's what we're going to look at next, and we can do that using our formula. Z equals X minus mu over sigma. And we know what Z is. We just found it, 1.35 equals, and then our X is what we're looking for. So X minus, and then we've got 3,000. And this is all being divided by the standard deviation, just 400. And then we take the 400 and multiply it. It's right now it's in fraction form, and we want to get the fraction. We want to get rid of the fraction, so we're going to multiply this side by 400 and multiply this side by 400, because that will help us get rid of the fraction, and we don't want to be working with fractions. So 400 times 1.35, and I'm coming up with 540 on the left side, equals, and then 400 divided by 400 is 1. So I'm just left with x minus 3,000 times 1, which is just x minus 3,000, and then we divide it by 1, and so it stays the same. And then I want to get x by itself, so I add 3,000 to each side, and then I get 3540 equals x. So what that means is this is the data point at the 91.15th percentile rank. We're seeing that at that rank, they're eating this many calories, 3540, and then we had the mean at 3,000. So that makes sense too. And then that is it. So if you have questions, please contact the course mentor for BEC1. We're very helpful here. And here is our email, nursingstats@wgu.edu, and we're happy to help you. So good luck with everything, and email us if you have any questions. Thanks. Have a great day. Bye. Hello, my name is Christine G, and I am just going to be doing this short video on percentiles. I'm using my kids as examples, how to use both of them. So my son Brendan ran the Stanford High School cross-country invitational, and the race had 213 people. He came in third for the cross-country 5K with a time of 15 minutes, 59 seconds. He was really excited to break 16 minutes on the cross-country 5K that had hills and stuff. Now the question asks, what percentile rank was he, and what does this mean? So when we look at calculating a percentile rank, this is something that's important to know. And we look at the number of data points below, or number of, in this case, runners, we could say people, below, and then total, so it's being divided by the total number of runners in this case, and then we multiply it by 100, and we get the percentile rank. So now we look at the information we have. Well, we know that there were 213 people in the race, and he came in third. So to get the number of runners that were slower than him, or weren't as fast, we would just subtract. He came in third, so there were 210 that were behind him. So we put that in the numerator, or the top of the fraction, and the total number of people in the race, well, that was 213. And then we multiply that by 100, and we'll get the percentile rank. So the way that I do this on my calculator is I just take 210, and then I divide it by 213, and then I hit equals, and then I get this long decimal. I don't take that out of there. I just go ahead and multiply it by the 100 to change it to the decimal to a percent. And I'm getting a decimal that goes on, so let's just put it, I'm going to put it to 0.59 to 591. Now, if they're asking me to round it or giving it in the nearest whole number or ones place, we would look at the number to the right of the 8, which is in the ones placeholder, and that number is 5, so it's 5 or more, so we would round up. So this is around the 99th percentile that he ranked for that particular race. Now, what does this mean? Well, that means he was ahead of around 99% of the people in the race. He was ahead of them, or finished ahead of them. And that means that he finished at 15 minutes, 59 seconds. So that means that there were only 2 people that finished, well, there was only, yeah, basically 2 people that finished ahead of him. And that, let's think about this, 99% of the people finished with a slower time than us. So I hope that makes sense. And then let's take a look at the next one. Now here I am talking about my other son because I have to be fair to both of them. And my other son, David, is a soccer defender, and he scored 1 goal and was ranked in the 15th percentile for scoring goals last season. So obviously he doesn't score many goals because he's a defender, but he still came up in the rankings. So as 15th in the 15th percentile, which is good. So we take a look at this and try and interpret what this means. So that means that he's ahead of 15% of the people that played soccer with him last season as far as goal scoring. So 15% of the people scored less than 1 goal. And the other side of that, 85% of the people scored more than 1 goal in these rankings and stuff. So hopefully this makes sense, and I'm just looking at trying to interpret these and seeing how that goes. Thanks.